Hello, in this video, I'm going to walk you through the Let language defined in chapter 3 of the EOPL book. And then we'll look at some test cases, and I'm going to tell you the layout of the code base, and we're going to look at how this is designed and then the tools that is being used in this language. So here's the Let language. It's a simple language to begin with, and but it uses the important principles we have discussed to design languages. So first of all, the language has its a concrete syntax, right? So the language is expression based. So the program, each program is a expression. So this is the grammar definition. So in this is the production rule format. So a program can be expression, is an expression. Expression can be a number of things. It can be a number by itself, a minus expression, subtraction expression, a zero expression, a if expression, or a verbal expression, or a let expression. So here are some concrete examples, right? So our program can be a number, an expression can be a number itself, can be a variable, can be a minus expression, which can be nested, right? So anywhere a value can be, it can be a valid expression. In this case, is another minus expression. We have a let expression. Let expression had this kind of concrete syntax. So it has a let keyword, a variable, a identifier, a symbol, equals a value which can be any valid expression. So this is recursively defined. And then in another keyword followed by a body. The body can be any valid expression. So it can be a let expression, so on and so forth. So now in this program, well, actually, let's look at this program. We define x equals to 5, and then we calculate, we compute x minus 3. So given the definition, this should result in a single value. Similarly, in this let expression, the inner let is defined in the body of the outer let. So in this context, x equals to 33. So this expression can be evaluated. Now we have another expression called zero expression. So this zero expression looks like this, right? So zero question mark open parenthesis, and then the in between the parentheses can be any valid let expression. This expression in this language. So we have a subtraction. So zero means the meaning of zero is if the input, if this expression is 0, then it's true, otherwise it's false, and this is needed by the if as a condition. So we can selectively evaluate either the then expression or the else expression, which can be any valid let language expression as well. So this can be nested. So this is it, right? So simple language, but has this a way to implement if selective evaluation, and we can do simple one math function, and we need a predicate for the if to work. Okay, so yeah, so those are the some concrete examples. So this is called concrete grammar, right? So this is the grammar user used to write the programs in this language. But then we the first step of interpreting this kind of program is to turn the syntax, the concrete syntax, which is here above, and then to something below. This is called the abstract syntax, right? We need to represent the programs as an abstract syntax tree. So we understand the structure of the program, so we can do the right things to them. So instead of using define data type, the tool, we're using a tool called SLLGen. It's discussing Appendix B. So it's the front end that generate abstract syntax trees. So basically, it is as if we have the defined data type ourselves, and it's called a parser generator. So given the grammar, we're gonna follow the format, the specification of SLLGen. If we do it correctly, this program, this tool is going to generate those defined data types for us, so we don't have to define this ourselves. We're going to look at the source code. So the end result is like this. So as if we have this defined data type. So we have seen examples using defined data type before. So here we're defining a type called a program, and we get a predicate for free, and then a program can be really is synonymous to expression. So it has one field, which is expression. That's how we represent a program in abstract syntax tree. And then everything in the tree is an expression, so which is another defined data type, a data type. So yeah, so okay, here's using the graph. We have one data type for each non-terminal. So our grammar, there are two non-terminals, so we have two defined data type. The SLLGen gonna give us two defined data type definitions, and then for each non-terminal there will be one variant for each production. So we have one production, another 1, 2, 3, 4, 5, 6 productions. So in the defined data type we have one for each non-terminal. There will be one variant for each production that has the non-terminal as its left-hand side. Each variant will have one field for each non-terminal identifier or number that appears in its right-hand side. So this is I think I copied from the appendix. So this is the rule that tool follows. So what does that mean? So for program, so this is one production rule, one data type for each non-terminal. Okay, so we have two non-terminals, program and expression. So we have two defined data types. For each non-terminal, there will be one variant. So for this one non-terminal, we have the one variant for each production. So since there's one production, there's a one variant, and then there's a naming convention. We program, this is the type, so the variant is going to be a program, and then the number of fields for each variant, it depends on what we have. So if we have a non-terminal, we're going to have a field for it. If it has a number identifier, we're going to have one field. If it has a number, it's going to have one field, right? So for as many of those, we're going to have a field for it in the variant. So for this one, for each non-terminal, there will be one variant for each production that has a non-terminal as the left-hand side. Each variant will have one field for each non-terminal. So this is a non-terminal on the right. So we're going to have one field, right? So that's all we need to remember about a program is expression that make up the program. Okay, so this is what we can imagine we get from the tool, so we don't have to type this ourselves. Define that type. Okay, so yeah, so this is the following. So for the diff expression, we needed two fields. Each one of this is a expression, the non-terminal, the data type we're defining, and so on and so forth, right? So that's kind of old information. And then we'll look at the source code. Oh, actually, let's look at the source code. So this is called the SLLGen is a front-end generator. So it generates not only the parser but also the tokenizer or the Okay, let me see the, okay, so actually maybe talk about this. So if you look at the implementation, the implementation are scattered in different files, each for a like functional component with this test file, which is pretty neat. So you could download the whole repository and load the, let's see, I'm gonna use the parser, okay? So this file has the parser functions procedures defined along with the test, so you can run the unit test to test this thoroughly. So here we're gonna use the SSLGen. So okay, so we use as to make define data type, and it takes the lexical spec and also the grammar. It's going to generate the define data type statements for us, the code for the definitions for us, and then it also give us this parser. So we're going to call SSLGen. So this comes from the SSLGen tool, and we're going to make a parser, give us define data type and give us the parser. So now so let's see what we have. The input to this are the scanner spec and the grammar. So the scanner spec is defined like this. This is how we define the lexical specification. So number is a digit followed by arbitrary number of digits, and identifier is a letter followed by any arbitrary number of letters. So the first letter has to be a letter, and then letter, then white space. Okay, and then here's the grammar. So this is the SSLGen syntax. So this really defines the concrete syntax, how to so this is all we need, or the SSLGen needs to create a parser for us. Okay, we're gonna try this out. So this is from the concrete syntax. So we have program can be an expression, and we call the variant a program, and then an expression can be a number, and then we call it a constant expression, and then let's see, so this is the field name, I think. Okay, and then so this is this is the concrete syntax. So now expression, if it looks like this, and then it's called a diff expression. We call it a diff expression and abstract syntax tree, and so on and so forth. So now this actually generates the grammar, the parser for us. Okay, so this is one part of the program. So we have a test. This uses the Racket unit testing tool. So we import it, and then we can run define some test cases. So let's see, we're gonna say if the program looks like this, we expect to get in our abstract syntax tree a program node, but underneath of the field is a constant expression. The value of that is gonna be 1. Okay, so that's our abstract syntax tree. For X, a symbol, a string that has 1 symbol, it's going to be a program with 1 variable expression. So if it's looks like this, if the program is a string of letters like this, it's going to be we're going to recognize or represent it as a program with a difference expression. The first part is a constant expression, and the second part is a variable expression. Right, so that's the parser, and then we have unit test with it. So now, okay, actually let's try this. So I'm gonna open my so I'm gonna open a new window, and then I will go to my file. file. Gonna open a file from my, so it's actually points to the folder where I download the code. So I'm gonna open my parser. So this is a implementation of the parser using our grammar. I can run it. Now we have some definitions. It's going to show you, as I have explained, this function call is going to create the defined data types. So let's try it. So so we're going to have a procedure or a type called program. So we're gonna have a predicate, right, created for us, or expression, and then also we're going to have so everything we expect here. So so we should be able to construct constant expression with a number or a variable expression is a symbol. So let's try that. So we got this from that defined data type generated for us. Right? So bar now it's gonna I have to give it a symbol. So that's that. So now let's try this. Okay. Also, the SSLGen give us this procedure called scan and parse. Given a valid program, a syntactically correct program, it's gonna give us the abstract syntax tree. Right. This is hard to read. It's in one line, but you can kind of see it's actually a tree, right? So program made up of diff expression, which is a constant expression, and then another diff expression, so on and so forth. So that's all that's generated for us, right? So with this tool, we can really simplify the parser generation part, right? We don't actually write the parser; we just passing the grammar. It's gonna create the parser for us. Okay, so that's one. And then as you read the chapter, we also, to evaluate the let expression, we need an environment. We need a way to to extend the environment, to store values, and to apply an environment to look up something. So that is defined for us, and so any of the previous introduced implementation could work. Looks like here we're using a list, what's it called? Associative list, a list of lists implementation, a data structure implementation. So okay, also it comes with a test, so where we test, so we use the extend environment to build this environment from an empty environment, and after that we can apply the environment and look for some symbols, and it should give us the correct value. Okay, so that is that, and then the next part of the piece of the puzzle is the interpreter. So interpreter looks like this. So to evaluate a program, we need to scan and parse it first, right? So given a string, we have a run method of function that procedure that given a string is going to scan or parse it and then pass the abstract syntax tree to a value of program. So a value of program is the evaluator program, the function. Given a program, a parsed program in this language, if it's a program, then we're going to call value of, and value of is really does the weightlifting. Given an expression, a parse expression, the initial environment, we're going to interpret this program. So as usual, we use cases to divide the different cases, the different variants, because the program is really just expression. Depends on what it is, we're going to do different things, right? So, and then we also have these extractors, the So yeah, our program actually, if you read the chapter, it's we use a data type called ExpressVal to represent the data types in our program. So we only have two data types. One is Boolean, one is number. So we have this extractor to get an expression express value and turn it into a number, so we can do math. And after that, we box it. We put it inside a num. Use this constructor to put it back in the data type we have. So okay, so you can look into this, and that is that. And then we have here's our defined data type for the express value, right? So for num value, those are just variants, right? We call num value, we call Boolean value, but inside there's just one field which is of a particular scheme data type. And then we have the extractors, and this give as the constructors, those functions are the extractors. And then there's a read, evaluate, and print loop that also yeah, so this we use the SFLGen. We can use it or we don't have to. And then this program, this piece of the puzzle also comes with a test file that thoroughly tests the different cases. And then yeah, we require interpreter, and then there's an initial environment where x indeed is associated with 10. So to run this program, so there's a run, let's see, important method called run, which is let's see, yeah, so it's here, right? So given a string, it's gonna run in parse and interpret the program. So inside it's gonna parse and scan and parse, but then it's gonna pass it to the value of, which is our evaluator function, and then that should give us the result of the evaluation, right? So run is the interface method. So now, okay, so that's the building blocks. There's one program, one file that has all, right? So this is has everything together. So if you load this program, you can run a bunch of experiments. So I'm gonna walk you through this. I have some test cases listed here, so we're gonna go over all of this together. I'm going to load all and run it. So this has all the building blocks, right? So there's a run. Okay, I'm going to show you the first one. Okay, it's run 42. So this is going to give us the result, right? So we have program input as a program, a string, and give us 42, which is in the expressed value format, right? This is a data type we use to represent values of our program. Of course, we can use the express val to num. Okay, we expect the num, and then this should give us the number as a scheme value. Okay, so let's follow my script, and then let's look at the result from an intermediate step. So what if we just want to parse it? So this gives us the abstract syntax tree, and built using the parser that is generated using the SFLGen tool, using the grammar for our language, right? So then run, we know run really calls the value of program function. So this gonna be equivalent to just call run, because run actually turned around, call these two procedures to get the work done, and then we can take the result and extract the number. We already done that. Okay, so now let's look at more complex program. So we have run. Okay, the program is overall is a let expression. where we define a variable equals to a value of an expression, and then we use that definition to evaluate the result. So this shows that our program interpreter is correctly defined, because now we can here. So if it's a let expression, we're going to let's just trace this. So if it's going to be a okay, after it's parsed, we're going to have a let expression as the abstract syntax tree, right? So we're going to take it, and when we evaluate it, we're going to take it apart with the var first expression, the body. Then we're going to do, the right thing to do is to evaluate the body of the let, but with the extended environment, in which the variable we are using in the let expression, which is x, should equal to 5. And val1 is evaluated first, right? We had to turn this into an actual value, express value, before we can extend the environment, before we can interpret the body. Okay, so that is the what happens behind the scene, and here's the test result. So now let's look at another test. This is more complicated. If you trace it, I think it's from the textbook, you'll get the correct value, which should be the number of value 3 of 3. So we have let expression outside of let, another let, another let. Okay, so it's the same. And imagine our evaluator gonna recursively evaluate this, right? Okay, we're gonna evaluate this let, let evaluate its body, and that's another let expression. So our interpreter is gonna just parse, walk down this tree, this abstract syntax tree, and to turn it to evaluate everything in the tree, so that we result in a single value, right? Okay. So here's a more complex with and then we have one that with the if, right? So let's try this. So this gives 18. So this imagine when this program is parsed, we're going to have abstract syntax tree. So at the root, it's going to be a let expression. Then its body is going to be another let. Then its body is going to be a if, right? So when it's recursively evaluated, so when if is evaluated, we're going to get to this part of our interpreter, right? So we take that if, that node apart, that give us 3 expressions. One that represents this, one represents that, and one represents that, right? All parsed already. Now, to evaluate this, we're gonna do what? Well, we'll need to evaluate this expression, right? The first expression. So we're gonna call value of with the current environment that give us a value. So, and then let's see. Oh yeah. So if, okay, so val expression 1 environment that give us val 1. Oh yeah. And then we're gonna make the decision. So we're gonna use the if in scheme, right? But if only operates on booleans, so we take it apart. We get the extract the boolean value, the scheme boolean value, from the express value of our language, the let language. And then if it's true, we're going to evaluate the expression in the current environment. Otherwise, we're going to evaluate the third expression in the current environment, right? So that is so it depends on what this give us. I think x is 33, so 33 minus 11 is 22. It's not 0, so we're going to evaluate that, right? So this is a simple minus expression. When we get to there, we have the value of y, which is when we evaluate it in the environment, and we're going to find y equals to 22, right? So, and then the second expression is 4 in the current environment. It's a constant. So we have val 1 is 22, val 2 is 4. Okay, So now we're going to use the let expression in scheme to define num1, num2, which is the numerical value of the two express evaluations. So it's going to be 22 and 4, and then we do the math because it's a difference expression, right? That's the right thing to do. So 22 minus 4 is equal to 18, and we're going to put it in make a num value, express value, num expressed value out of this Boolean, the scheme value. So we're using the constructor from our defined data type somewhere here, defined data type, right? So it's a num value. And then of course we have a way to take it apart and get the number out of this num value as a expressed value. So it's a little bit complicated, but that's how this this example works. So we're gonna expand this in the future to make it do more and more, but this is the basis of the future discussions. Okay, so that's it.